Imagine you are driving as you do every day, but the road beneath you is no longer on solid ground. It is deep beneath the ocean floor. Above you, there is no sky. Only millions of tons of seawater exerts constant, crushing pressure. Surrounding you is a tunnel of concrete and steel, assembled with near absolute precision, where even the slightest misalignment could trigger a catastrophic failure. It sounds like science fiction, but this is reality. So the question is, how do they construct such colossal tunnels beneath the sea? Watch till the end to discover the technology and construction secrets behind these engineering marvels, and see how they make the impossible possible. Every megastructure begins with a bottleneck that legacy solutions simply cannot resolve. In the 21st century, transportation is no longer confined to land. It has expanded across the maritime domain, where logistical flows dictate the pulse of the economy. With over 14,000 kilometers of coastline and hundreds of port cities, China has constructed the world's largest maritime system. Every passing minute, thousands of containers depart from its ports. A continuous flow. Approximately 60% of the global economy depends on this very system. But this success poses a massive challenge. How do you maintain a seamless connection between the mainland and the islands, independent of weather, ferries, or bridges? In port clusters like Zhuhai, Shenzhen, and Hong Kong, this problem occurs daily. A single storm or dense fog can instantly paralyze the entire transport network. It's not just cargo that is delayed. The global supply chain suffers the consequences. The solution? Not aircraft, nor traditional cross-sea bridges. The answer lies in constructing undersea tunnels, piercing through the seabed to link the mainland with distant islands, creating subterranean arteries that ensure traffic never stops. This is the undersea tunnel of the Zhuhai-Hong Kong link, a critical component of the Shenzhen-Zhongshan mega project. Of course, to build a tunnel beneath the seabed, you don't start with concrete or excavators. You are forced to take a detour. Why? Because beneath that seemingly calm water lie thousands of years of geological movement, where layers of rock, mud, and sediment shift millimeter by millimeter every year. One wrong move, and the entire structure could collapse instantly, like a game of Jenga. That is why the pre-construction phase is viewed as a comprehensive diagnostic surgery, where every risk must be identified before a single shovel hits the ground. No random test drilling. Everything is data-driven. The process begins with seabed topography surveying, using specialized vessels and sonar technology to construct a detailed 3D model of the entire area. Every ripple, every deep trench, all reconstructed with near absolute precision. Next, small-scale drill bits are lowered to collect soil samples, testing for load-bearing capacity, stability, and corrosion rates over time. But that isn't the most dangerous part. Engineers must also hunt for hidden hazards, such as geological faults or methane pockets buried deep within the sediment. One accidental strike, and the result could be an explosion or uncontrollable subsidence. How can they be certain they haven't missed a single risk under dozens of meters of water? The answer is redundant testing, multiple locations, various depths, until every variable is plugged into the calculation model. But simultaneously, another equation emerges. How do you build without destroying the surrounding marine ecosystem? The ocean is not a void. It is a living ecosystem. Construction noise, vibrations from drilling, or seabed dredging can cause direct harm to marine life, especially sound-sensitive species like whales or dolphins. Therefore, control measures are deployed from day one, including noise reduction, acoustic absorption systems, and real-time biological monitoring. In some projects, artificial coral reefs are even constructed to compensate for affected habitats. Not just construction, but adaptation. This is no longer a mere engineering project. It is a process of negotiation with nature, where every decision must balance performance with ecology. One small surveying error or a noise level exceeding the threshold, and the entire project could become a disaster. After completing the survey phase, China entered the most difficult part of the project, turning data into a physical structure beneath the ocean. No more simulations. The first chosen method was the immersed tube method or technique, involving the assembly of massive prefabricated tunnel segments manufactured on land, then lowering them to the seabed with near absolute precision. Each segment was about 217 meters long and weighed up to 73,000 tons, equivalent to a block of steel and concrete nearly the size of a large ship. Colossal. However, the highlight was not just the size, but the fact that these segments had to be produced in a strictly controlled environment. Tolerances were kept to a minimum to ensure that when joined underwater, the connections would be perfectly airtight. Not a single gap. The construction process began by towing the segments out to sea using a floating system, then precisely positioning them over a pre-dredged area on the seabed before lowering. Slow, but absolutely precise. A deviation of just a few centimeters during placement could destabilize the entire structure and lead to severe risks later. To ensure the segments connected safely, engineers used specialized rubber gaskets compressed tightly at the joints to prevent seawater from entering. But even when everything was sealed, an invisible force remained that could not be ignored. Archimedes' principle. The constant pressure of the seawater creates a tendency to lift the entire tunnel, similar to how an object floats in a liquid. Therefore, to keep the structure resting on the seabed, a thick layer of sand and gravel was backfilled over the top. This provided enough weight to counteract the buoyant force throughout its operational lifespan, pushing down, locking in place. At this point, the entire system functioned as a stable structure, resting on the ocean floor while enduring continuous environmental stress. But the immersed tube method is not always feasible, especially when seabed terrain becomes complex, or currents are too strong to control the segment's positions accurately. Cannot be anchored, cannot guarantee accuracy. What do you think happens if this entire massive tunnel shifts just a few centimeters from its design? That is when engineers were forced to change their approach, shifting from assembling blocks to creating the entire tunnel directly beneath the ground, no longer lowering, but boring through. This is when the tunnel boring machine, TBM, appeared. Giant drilling machines acting like autonomous robots, piercing through rock and sediment to forge a complete tunnel right under the sea. With a colossal length of over 100 meters, a cutting head nearly 12 meters in diameter, and a weight of thousands of tons, the TBM is the most formidable construction machine on the planet. A literal steel worm. This method is deployed when seabed terrain becomes too complex, where immersed tunnels cannot guarantee the necessary stability or precision. Imagine the TBM's circular cutter head, fitted with over 140 high-strength steel blades, rotating continuously at nearly 3 revolutions per minute to pulverize every layer of rock and soil in its path. Slow but unstoppable. The compression pressure from the cutter head can reach up to 400 bar, enough to shatter hard limestone, thick clay, and complex sedimentary layers deep beneath the ocean floor. But what makes the TBM extraordinary isn't just its mechanical brute force. It's the fact that it operates like a miniature factory underground. In soft or water-saturated soil, engineers inject a mixture of foam and water into the excavation chamber to create a pressure balance between the interior and exterior of the tunnel. A seemingly small detail, but it is a matter of life and death. If the pressure is unbalanced, the tunnel walls could collapse instantly as water and soil flood the interior. The entire sequence, excavating, installing tunnel linings, grouting, and propelling the machine forward, it is integrated into a continuous, synchronized loop within a closed system. Uninterrupted. After every 1.5 meters of excavation, the system automatically installs precast concrete segments and pumps grout to seal every gap between the structure and the surrounding soil, step by step, achieving absolute unwavering precision. On average, a TBM advances at a rate of approximately 15 to 20 meters per day. While this may not seem fast by conventional standards, it is the optimal speed required to ensure the long-term structural integrity of tunnels that span tens of kilometers across the abyss. However, the tunnel boring machine is not always the optimal choice, especially when geological surveys reveal ultra-hard rock layers or underground gas pockets with abnormal pressure. Dangerous. In these conditions, the TBM's cutter head could be destroyed or lose total control during operation. That is when the construction team is forced to revert to a more traditional method. Controlled drill and blast. It may sound primitive, but in reality, this is an extremely precise physics equation where every millisecond is calculated to avoid compromising the surrounding structure. The process begins by drilling a series of deep holes into the hard rock, followed by placing explosive charges according to a meticulously designed diagram. They don't detonate all at once. They follow a sequence. The detonators are triggered just a few milliseconds apart, creating a chain reaction that breaks the rock efficiently while minimizing the spread of seismic vibrations. A single blast can clear about 1.5 meters of rock, and in a single day, this process can be repeated from 15 to 18 times, depending on the actual conditions. But in your opinion, what is the real danger in this method? It isn't the explosion itself. It's the aftermath. Each detonation sends shockwaves through the geological layers, which can cause microfractures invisible to the naked eye. If not reinforced immediately, these cracks could spread and threaten the overall stability of the tunnel. Not to mention, in a subsea environment, the pressure and vibrations directly impact the surrounding ecosystem. Sound, pressure, all can harm marine life, especially species sensitive to environmental fluctuations. Therefore, the drill and blast method is always strictly regulated in frequency, intensity, and scope of impact throughout construction, only used when necessary, when all other options are non-viable. And that is what makes drill and blast the final resort, where the line between control and catastrophe becomes thinner than ever. Beyond the high-tech machinery, there is a primitive-sounding method that no one expects, yet it becomes the final resort in the harshest conditions. The fail-safe option. When immersed tubes cannot be lowered, when a tunnel boring machine cannot be operated, and when explosives are too risky to detonate, engineers are forced to return to traditional excavation techniques to keep the project moving, meter by meter. But this isn't the manual labor of the past. It is a construction system controlled with extreme rigor from top to bottom. The process begins by sinking a vertical shaft from the surface, piercing deep into the construction zone to create a direct access point. From there, hydraulic cutters are deployed to break through soil and rock, while reinforcement systems operate almost simultaneously to stabilize the surrounding structure. Cut, reinforce, advance. Immediately after each excavation step, shotcrete, sprayed concrete, is applied to the tunnel face, combined with steel arches and anchor bolts to ensure the structure does not collapse. Zero lag time. Everything must happen instantaneously. But what is the most dangerous factor in this method? It's not the machinery, it's the pressure. In a subsea environment, external water pressure is significantly higher than the pressure inside the tunnel. Even the slightest pressure differential can cause water to breach at catastrophic speeds. A tiny margin of error, a massive consequence. That is why the entire system must be constantly monitored by pressure sensors, relief valves, and real-time warning devices. Engineering teams are on standby 24/7, tracking the smallest parameters to ensure the pressure balance is never breached. Zero room for error. And the most important takeaway is that this method doesn't exist in isolation. It is part of a flexible construction strategy where techniques can shift constantly depending on real-world conditions. Adaptation. That is the true deciding factor of success. When the final meters of the tunnel are linked deep beneath the sea, many think the job is done, but in reality, that is only the starting point for a system that must operate flawlessly for decades. It is far from over. An undersea tunnel must do more than just stand firm on inauguration day. It must endure constant pressure, humidity, temperature fluctuations, and geological vibrations that shift over time. Therefore, following the structural phase, engineers move to a more critical step, transforming the tunnel into a closed operating ecosystem. Not just a passageway, but a living system. The entire tunnel is divided into two independent traffic decks, doubling the flow capacity without increasing the excavation footprint. In between, emergency exits and ventilation systems are interspersed, ensuring that a safe access point is always within 200 meters. Fast, precise. Inside the tunnel, waterproof and anti-corrosion LED lighting operates 24/7, combined with anti-slip surfaces and drainage systems to handle any potential leakage. Every 100 meters, sensors and infrared cameras monitor air quality, detecting smoke, fire, and vehicle incidents almost instantaneously. But the most vital part isn't what you can see. It lies behind the concrete layers. Thousands of sensors are installed along the entire tunnel length, continuously measuring pressure, humidity, temperature, and vibrations transmitting data to the control center in real time. If any abnormality appears, even the smallest tremor, the system immediately alerts and triggers an inspection protocol. Early detection, resolution before failure. Simultaneously, autonomous maintenance robots travel along the tunnel, using sensors to inspect blind spots that are difficult for humans to reach. In some cases, they can perform on-site repairs, minimizing downtime and traffic disruptions. Self-inspect, self-maintain. Furthermore, the safety architecture includes automated barriers, high-output ventilation fans, and rapid response mechanisms that can activate within seconds of an incident. AI is even utilized to analyze vehicle behavior, predicting risks before they manifest. But do you believe technology can completely replace humans in such a complex system? The answer is no. Behind it all remains a team of engineers monitoring 24/7, ready to intervene the moment the system encounters a glitch. Technology operates, humans control. And it is this synergy that transforms undersea tunnels into structures that are not only durable but also capable of adapting and self-healing over time. On June 30th, 2024, after 7 years of continuous construction with extreme technical complexity, the Shenzhen-Zhongshan megaproject was officially put into operation, marking a significant step forward in subsea infrastructure, a historic milestone. This is not just a single transportation route, but a complex of bridges, islands, tunnels, underwater connections, integrated into a single system, where each component must operate synchronously with near-perfect precision to ensure the entire structure operates stably. A seamless structure. Out of a total length of over 24 kilometers, the subsea tunnel section alone accounts for 6.8 kilometers, positioned 39 meters below sea level under extreme pressure in a constantly changing environment. Hidden beneath the ocean. This tunnel is designed with 8 lanes, 4 in each direction, making it the widest steel shell concrete immersed tube tunnel ever built in the world. This figure represents not just size, but a very high level of structural control capability. An engineering record. The entire structure is designed to withstand a magnitude 9 earthquake with an expected lifespan of 100 to 120 years, requiring a perfect combination of materials, design, and monitoring systems throughout its life cycle. Sustainable in the long term. But the true value of the project lies not in technical figures, but in its direct impact on regional connectivity and the economic system. This tunnel has reduced travel time between Shenzhen and Zhongshan from about 2 hours to just 30 minutes, creating a clear shift in how people and goods move between economic centers. Faster, more efficient. Beyond transportation, this project has become the backbone connecting the Guangdong, Hong Kong, Macau, Greater Bay Area, one of the most dynamic developing regions in the world today. A unified network. Spillover effects emerged quickly as logistics costs dropped, tourism grew, and high-quality human resources could move more flexibly between tech cities. A chain effect. More importantly, this project has demonstrated that China can master large-scale immersed tunnel construction and tunnel-based boring machine technologies, thereby creating a foundation for expanding and exporting this infrastructure model to international markets. A statement of capability. What do you think about these undersea construction technologies? Which method impressed you the most? Share your thoughts in the comments below. We'd love to hear your perspective. If this video gave you a deeper insight into modern engineering, don't forget to subscribe to Massive Tech. Join us as we explore extraordinary technical feats, where every structure is a heroic epic between human intelligence and the limits of nature.